Uh, we're in chapter number 3 and 2. I'm going to try to recap everything. You guys have been watching videos and from YouTube that I've found online, and hopefully the concepts are resonating a little bit and it's making sense. Needless to say, this isn't my favorite thing. I'd like to see you guys sitting out in front of me instead of a bunch of empty chairs, but it's kind of like having a date with your mother. You know, you accomplish what you went to. You saw the movie, but you're not very excited about it. Be nice to have you guys out here so I could get a little body language and watch your faces and see where you're at, so I could try to get a pulse and maybe change a few things so that you've got some more information. But it is what it is, unfortunately. So what I thought I'd do is do a little bit of review and a little bit of reinforcement and get us through chapters number 2 and 3. That's what will be on the test. And we are going to eliminate chapter 3.9. I took it off of the canvas. When you look at it, it'll go down and you'll see homework number 12, and then you'll see a gap in homework number 14. Homework number 13 was 3.9. So you can take and cross it off of your syllabus. It won't be a problem you'll be doing. It's a concept that I wouldn't mind getting to you, but it's a concept that I don't think is going to have a tremendous impact on anything the rest of your life. So based on time, I decided not to attack that section. So first thing I'm going to do today is just do a shear and moment diagram. Make sure you got the concepts down. Then I'm going to go into chapter 5, or 3.5, and show you how to use the tables. And then we've got a couple more things. So hopefully by the time we get done, you'll have the concepts down. Okay, I took this guy. It's a beam. It's 10 foot between supports, 2 foot overhang on the right. It's got a uniform load, and that uniform load is 500 pounds a foot. And it's got a couple point loads, one in the center of between the supports and one at the end of the overhang. So your first task is going to be figuring out what these reactions are. And if you took this guy, which is a hinge, you would take this and you'd put a force here and a force there. And I call this point A, so I call this AY and AX. And then over here, I've got a roller. Roller is this, and I call that BY. Okay, now I've got arrows, and unfortunately I've got arrows that are little baby guys that I don't need, and I would like to replace them with one big arrow. So I'm going to take and find big W by multiplying 10 plus 2, 12, times 500, which is 6,000, and it goes dead center. So I'm going to put this guy right here, 6,000 dead center. And it looks to be a foot off of the 4,000 pound load. Okay, quickly, sum of forces in the X, there are none. Sum of forces in the Y have to add up to 0. It looks like I've got AY going up, 4,000 going down, 6,000 going down, 1,000, or BY going up, and 1,000 going down. So AY plus BY. I'm going to go relatively quickly so we can get to the meat. There, 11,000. Some of the moments, and I picked A. I put a nail right at the beginning. I've got 4,000 times 5 going with the clock. I've got 6,000 times 6 going with the clock. I've got 10 BY going against the clock. I've got 12 1,000 going with the clock. And when I take those and I add them all up and I do the division and I get everything where I want it, I got 6,800 for B. When I take the 6,800 and throw it right back into that hole and subtract it from 11,000, I get 4,200 for A. So I come over here and I put 4,200 right here. And I put 6,800 right here. Now I'm ready to draw the shear diagram and moment diagram. Once again, same thing every single time. Shouldn't waver at all in your brain. Wherever there's a reaction, drop a line. Anywhere there's a point load, drop a line. End of the beams, drop a line. Got one, got one. And anywhere there's a change in load, there isn't a change in load here. Notice I didn't worry about this 6,000. It's in red for a reason, for summation purposes only. So after you've got your reactions, you want to do this mentally or physically. You want to get rid of that because that's really not part of anything we're going to do from here on. Okay? So I've got it now back to the original state. And I've done everything I said, ends of the beam, anywhere there's a reaction, anywhere there's a point load, anywhere there's a change in load. First line is going to be a shear diagram. Starts out at 0, anything above the line is bigger. Starts, anything below the line is smaller. Starts at 0 and ends at 0. Notice the X did not go where the support was. It goes at the end of the diagram. So starts at 0 on the left, stops at 0 on the right. Do exactly what it says. It says go up 4,200. It says drop 500 pounds a foot for 5 feet. 2,500. 2,500 from that should end up with 1,700. Drop 4,000, that should put me at minus 2,300. Drop 500 pounds a foot for 5 more feet. That's 25, so that means this is minus 4,800. Jump up 68, 2,000. 500 pounds a foot for, let's see, what do I have here? 500 pounds a foot for 2 feet. That's 1,000. And drop 1,000, I'm back to 0. Okay, if you've got a horizontal line on the curve above, horizontal line, it means it's decreasing or increasing at a constant rate. In this case, it's decreasing at a constant rate. Constant rate decrease is a straight line. So I'm going to take and go up with the arrow, slope, down with the arrow, slope, up with the arrow, slope, down with the arrow, close. Okay, if I drew this right and I calculated my reactions properly, I end up with a curve that has areas that are equal. Anything above the line, this area plus this area, has to equal that area. So I take the 4,200, add the 1,700 to it, divide by 2, multiply by 5, I get 14,750. 2,300 plus 4,800 divided by 2 times 5, I get 17,750. And 2,000 plus 1,000 divided by 2 is 1,500 times 2 is 3,000. At this point, I can take and I can add up the pluses. 14,750 and 3,000. And I can add up the minuses, and there's only one, so I can't mess that up too bad. They're exactly the same number, and that's what I want. That means it's going to close. And it means that I've calculated the reactions properly. Next is the moment. Above, bigger, start at 0, end at 0. Plot it. We talked about this a minute ago. I'm pretty sure I've already had this video. The change in moment between any two lines on the moment diagram is equal to the area of the shear diagram directly above it. So, the change in moment between that line and that line is a positive 14,750. I started at 0. I add 14,750 to it. I'm at 14,750. Okay, the change in moment between this line and this line is that area. So I got a positive 14,750. I add a negative 17,750 to it. It gives me a minus 3,000. And then the change in moment between this line and this line is that. Start out with negative, add 3,000 to it. I'm back to 0, perfect. Now I create the curve. And once again, if I divided this into 5 equal segments, you can see that the areas keep getting smaller from left to right. This area right here is much smaller than this one, or bigger than this one, excuse me. So they keep getting smaller. It's increasing because it's on the positive side of the line. It's increasing at a decreasing rate. That is a parabola. It's increasing at a decreasing rate. 5 equals, each one keeps getting bigger, decreasing at an increasing rate. Starts out slow and goes fast. And the last one is increasing at a decreasing rate, starts out fast and goes slow. So there's your shear and moment diagram, and we need the biggest shear and the biggest moment. So I look at the shear curve and I look for the biggest absolute value, biggest number. 42, 23, 48, 2,000. Looks like this 48's a winner. V max. It's 4,800 pounds. Okay, down below, looking for the biggest number. M max, maximum moment, is 14,750 foot-pounds. That's it. So hopefully between the videos and my couple of examples, I'm going to do another example with a cantilevered beam. You can find the moment, and of course the moment is derived to fit into these equations. And the shear is meant to fit in this equation. There's your shear, there's your moment. So if I was doing this problem, that number would go right there, and this number would go right there. And then the rest has to do with cross-sectional properties. Okay, hopefully you got that. Now I'd like you, while I'm erasing this, I'd like you to turn to page 114 of your text. And when you get there, you're going to see a page that has a bunch of pictures. They call them cases. And each case has a little scenario. These scenarios replicate what the real world has to offer. We have quite a few of those out there. So, if something's already been done and can be done easy, there's no use messing around trying to get ourselves in a position where we recreate it. So I'm going to do problems. I'm going to do problem 3.5a and 3.5c. Okay, let me tell you what you got to do. You got to be able to read the problem and figure out which case it is. Okay, so that's your first quest. So read the problem. when you're reading it, hopefully you're drawing a little picture in your head. It says it's a simple span beam. That's this in my world. Simple span beam. It has two concentrated loads of 4 kips placed at the third points of a 24-foot span. 24 feet. Third of 24. 8, 8, 8. And they're 4,000 pounds each. Okay, now you take a look at the pictures and you find one that makes sense. To me, case 3 makes sense. You go to case 3. And you take case 3 and you look at the picture and you say, okay, it has a P here, and an L here. Okay, and it also has 2 equations. PL over 3, M equals PL over 3, and V equals P. Okay, this is P, right here. P is not 8,000. Students have a tremendously hard time understanding the fact that P is P. P is not 2P. Okay, you don't add them together. That's P, 4,000. L is 24 feet. So all you got to do is this. There's your maximum moment. And this is a toughie. I screwed it up, even it's so tough. That's it. That's all there is to it. So understand that P is P, not the sum of the P's. Okay, the second one is, you're doing B and D. Simple beam, span of 32 feet. So I'm going to draw him. Simple span, 32 feet. That's L. It has a, it has a concentrated load of 12,000 pounds, 12 feet from one of the ends. Find the value for the maximum bending moment. I'm going to do the shear too. So in my world, it's that. Okay? Now I'm looking for a picture, and I wander through and I get to case 7, and it looks pretty interesting. So case 7 looks pretty good. And then I put the letters there. This is P. This is A and B, so this is A, and this is B, and the whole thing's L. And it says there, make sure that A is less than B, 12 is less than 20, I'm okay. Write down the equation, M equals